For today's talk, we wanted to show you how to build your own RAG infrastructure with OpenSearch. But before we get into that, my name is Pedro Sousa. I'm a solutions architect at Canonical. I've been here for roughly 5 years, and I work with some large organizations in and around Europe designing solutions, open source solutions, and implementing those solutions for them. Organizations like governments, NGOs, so on and so forth. And today I'm with my colleague, Pedro. Pedro?
Hi, everyone. My name is Pedro Guimarães. I work at Canonical as a software engineer. I've been there for several years. And I've been working with open source for almost a decade now, designing, implementing. Right now, we are focused on data platforms. I'm on the OpenSearch team, building an operator to automate the lifecycle management of OpenSearch, and I've been there for the last few years. So we're going to talk about this operator later as well. Peter?
Yeah, so when we were preparing this talk, there was a question that we wanted to answer. At the time, there was there was a lot of kind of attention around RAG and how this could be achieved. And we wanted to see how could we do this in a secure and scalable architecture, which is also open source and enterprise ready, of course. Now, we'll talk later I'll talk later on in the presentation about how we actually do that practically with the operators. But before we get into that, Pedro is going to talk to you about some of the background and the context around that. Pedro?
Yeah. So I'll be honest with you. I'm going to start with a quick summary. I'm pretty sure here in the audience there are people that are way more versed into the search and the engines behind the scenes. So this is just a quick summary the way we are seeing from when we look at into the LLM market. We started with document indexing algorithms like BM25, DDIDF, OpenSearch is there, Lucene is also here. I remember a talk I've seen from Doug Cunning a while back, and he was saying like how the websites are all using either Lucene or some sort of library that provides these document indexing and word counting, word frequency functionalities. Pretty much every website except the internet scales, right? So Google, for example, Facebook, of course, they develop their own search engines. Of course, downloading all the internet and just counting frequencies of terms will not be enough. They had to find other relationships to figure out which document is more relevant for a search. That's where, for example, PageRank is, although proprietary, is one of the algorithms that stands out in that second phase, let's call it. You can think of Facebook as well when they released FIEs, right? And that allows us to convert things like pictures into vectors and do search into that vector space to find the pictures that are related to your search. And now we are entering this third phase, which is the conversational. So we have OpenAI, Claude, DeepSeek, etc., that are able to actually answer our queries with a summary of an answer. And behind the scenes is the large language models. Roughly, we could say they are like a very big extension of NLPs, right? Natural language processing, where you are essentially guessing the next word and word. But given the sheer size of these neural networks and the sheer amount of data they were trained, they are able to give entire paragraphs and entire big summaries of our queries, right? And to the point, actually, I've been seeing a lot of that, especially on LinkedIn and etc. People asking, is the computer understanding us? Of course, this is not the topic here. What I want to talk actually is how can we bring these LLMs into a corporate environment, into a given industry, for example, banking, governments, etc. And when we go into these environments, what we're going to have there is, yes, we need to have the LLM, but we also need to have a way to bring documents from these users and customers, right? And that's where, for example, the RAG, the Retrieve Augmented Generative AI proposed by Facebook was so powerful. It essentially breaks that task into two. So we have the retriever, and then you have the generator, which is the LLM essentially, where the retriever can, based on a query, search in a knowledge base, like a vector database, retrieve the context of that query, so documents around it that make a lot of sense, and then send to the LLM to generate an answer based on that documents. Now, if we look a little bit further, how could we outline an architecture? We took this from the OPEA. It's a Linux Foundation initiative. And they break that high-level picture into more functions, right? So there are several functions happening here. And starting with the enterprise data, so that's the secure data we want to protect. We ingest that. And then we go through the embedding model, which essentially converts these documents into vectors that can be saved into a vector database and made available for search. That would be essentially kind of the first pipeline of the whole RAG process. And there are essentially 3 pipelines there. So this is the first one. The second pipeline would be the user processing, essentially. So user makes queries. And these queries first hit a guardrail, which is either a model or, for example, a functionality on OpenSearch, which actually is an OpenSearch API, so we can have excluded terms out of search. And the question that guardrail is trying to answer is this query harmful for our system? Is this query harmful for our reputation, for example? And once you pass this guardrail, then we make a retrieve into the vector database. We retrieve, so that query gets embedded. And we retrieve all documents around that query that are relevant. And that builds us a bigger context, which then we can generate an answer with the LLM. And with that answer, you have that more information around the context of the company, right? And the third pipeline is the user feedback. So that is going to be more manual, essentially, because after the search is responded, then the user can provide, if that query was correctly answered, for example, can provide a feedback and write something to you, and then you're going to have to go through that data. That third pipeline would be essentially when you, for example, decide to fine-tune a model, decide to change an embedding model, decide to take these decisions, and close the loop of this data platform where you refeed all these building blocks, these functions here. Now, this is a very nice architecture. It's very real for us. And the question we wanted to answer at Canonical is, OK, how can we make it with open source, given we are an open source first company? And after looking into the landscape, after testing some tools, we got down to 2 main tools for us, OpenSearch being one, and essentially running the 2 pipelines as we discussed. And then we can have Kubeflow there at the very end. Kubeflow, for those who don't know, is an AI pipeline manager. So you can receive your data, train your models, and then serve these models, which means picking a model that you trained and putting it to essentially a REST shell, and then you can interact with that model. Why did we decide for OpenSearch is because essentially this whole ingestion pipeline is the core of OpenSearch, right? So we submit all the documents to OpenSearch. It gets embedded using a model, using an ingest pipeline. And we have an embedding model that gets transformed into vectors. We save all these documents into a vector database. And then when the user decides to query, we can use the guardrails functionality to decide if that query is somehow harmful or not. Should we abandon it or not? And if not, then we can send you a prompt and retrieve into the vector database that context of documents that make sense for your query. One of the things we've been testing with is OpenSearch, and it has released an integration with Intel AVX, so that gives us a good performance bump. So that was one of the good sides of adopting OpenSearch. There is the vector database, besides keeping everything on a single component. And essentially, that prompt processing can be integrated with Kubeflow on that last stage where Kubeflow can serve your model, right? And you can interact with it, send API requests, receive your question, receive your answer back, and then return to the user, crossing again the guardrail to make sure your answer is OK. The third pipeline, again, is a user feedback, so it's a bit out of control of these tools. But once you get that feedback, you can take a decision. What Kubeflow brings extra here is not only a training and a pipeline management, right? It also contains things such as a repository where you can train, fine-tune your LLM or train another model that you are interested on and keep the records of how these versions of your model compare to each other. We talked about the two open source solutions, OpenSearch and Kubeflow. Why OpenSearch and Kubeflow, actually? So first of all, they're very stable open source projects with a health community, each one. They have API to answer any RBAC. We can use all the RBAC and APIs that OpenSearch has besides the actual data processing. We have the search, vector search with KNN, memory. We have all the functionalities of OpenSearch integrated with LLMs. And for Kubeflow, we have Kserve, and we have other functionalities for you to, if you want to train your model, if you want to train any model, actually, it will provide you with a very good management of your pipelines. Question? It will provide you with a good pipeline management, so you can, fine-tune your model. OK, so we answered the question having a RAG, and how can we make it with open source. But now we need to bring it to actually real industry. So let's imagine, for example, a banking industry. The first thing they will look for is this environment secure? So we took some knowledge out of David Wheeler. He was, essentially, we could summarize 3 main issues, security issues that we should look for when we are deploying these models. Of course, each of these points we will eventually could be a talk on themselves. So we're going to focus on one of them and just highlight some others. So evasion, of course, do the right thing. We have the guardrails. It can be just this simple guardrail with an exclusion list, or it can be something more sophisticated. But it's essentially sort of a semantic firewall in front of your RAG. Then you have pipelines. If you want to train your data, there you need to curate your data. It's a manual process, right? You need to be careful with the data you have, make sure you went through that, and you can use pipelines to train. I don't want to really focus on these two, and I wanted to talk more about the loose confidentiality, because we are actually providing you with a data platform, so first, and that's where you're going to be actually spending most of your time. So you are training your model for 1 month, and then serving it for 1 year, 2 years, etc. And when we look into how we could lose confidentiality, we could highlight 3 main topics, right? Data at rest. So we want to be sure the data you stored on your platform is not, if someone pulls off a disk, for example, of your servers, you still cannot read the data. I think that's pretty clear. Data in transit, so for example, we have a TLS. That's also very well established with TLS, PKI. The problem of those 2 topics is not what should you use to implement them, but actually, how can you manage the life cycle of data at rest and data in transit? So how can you answer questions such as, what if my key is compromised? My encryption key of the data of your disk is compromised. How can you change that key and still keep your platform running? How can you keep your availability? How can you do CA rotations and still have a platform running? How can we automate that? We're going to go into these 2 topics with our operator. And finally, data in use. this is sort of the new technology. It's the confidential computing we've been experimenting with, which enables us to, first of all, if you're running your VM, you can encrypt your memory and make sure that even if, for example, the host of that VM has been compromised, you cannot, whoever tries to read that memory or dump that memory cannot read your data. And you are also running on a trust environment, or as in confidential compute is called, an enclave, where is a trust section of the CPU. That's for the encryption side. So when you are running, you're still running safely. And you can also generate attestations. So you can look at your system and generate an attestation if that hardware is secure. And then you can even trade that attestation with other nodes. So for example, you can send, not now, but there are discussions in communities. So you could, for example, send that attestation to another node and present yourself as, like, not only you are safe as a process, you are trusted via TLS and the CA, but you also trusted the environment that you're running. So you can present an attestation that you're running on a safe environment. What that attestation looks for is measurements of your CPU, as they call it, which are the root of trust. So are you running on a safe hardware, with a safe, which firmware, software, bootloader configurations, etc., and generate an attestation out of it. There are technologies in the market already. Intel is the one that I personally had experience, the Intel TDX. And then you can, with that, guarantee that your VM is safe, even if it's an unsafe hypervisor, or if you have, for example, another VM that's a neighbor, and that VM is a malicious user. And you can essentially trade or send that information with other nodes. Now, at the end, to summarize what that gives us, so it's a encrypted memory. So we are ensuring our memory is safe, secure from potential breaches, and especially from a case of a malicious user having an administrator access level. You're still safe because that user cannot dump your memory and see your content. Now we're going to talk about the other topic, which is scalability. And for that, I'll give to Peter.
Thank you, Pedro. So Pedro's introduced the kind of background here of how we can architecture this conceptually. And what I want to talk about is how we can do this in practice. So with our government or our banking institution, we want to make sure that we can scale up and down as we need to. We want to have automated large deployments, and we want to observe those deployments as well, because obviously we want this thing to be maintainable. We want it to be manageable, right? So how do we do that? Well, the way I want you to think about how we do things at Canonical and with operators is nodes in a graph, right? So Canonical's been creating operators for over a decade now. We've been working with open source for 20 plus years, and we've been refining this process. And what we've come to is this event-driven architecture with Python operators, which respond, sending and receiving data, containing configuration and metadata in that graph, right? So in the slide here, you can see a very simple example of an operator taking and responding to taking data and responding to events. What this allows us to do is to integrate those tools together. So taking the OpenSearch operator, we can combine that with a TLS operator, and this will then give us what Pedro spoke about earlier, the data in transit security. So now we're adding nodes to that graph, right? So we've added 2 nodes. We've got our OpenSearch operator and the TLS operator. And they can then respond to TLS rotation events, certificate changes, CA changes. What we're doing is we're taking that that life cycle and we're converting it into events. I apologize. I didn't mention Juju. So just on Juju. So Juju is Canonical's open source integration and lifecycle management solution. So it works at any scale on any infrastructure, so Kubernetes, VMs, etc. And this is what drives these operators, including the OpenSearch operator. But going back to this example, we're just responding to those events and building out that graph. So taking this further, we can then start to build larger architectures, larger deployments, as we call them. So now we want to productionize what we've created. We want to productionize our architecture, and I'll show you some more examples of how this can be achieved in Juju and operators in the next section, in the next slides. But in effect, what you can do today with the OpenSearch operator is to give it different roles, right? So in the architecture diagram here, we have data hot, data cold, cluster managers, data frozen, and ML. And what this allows us to do is create instantiations of that operator with different purposes, right? And then again, we're just extending that graph, connecting or integrating it all together, and allowing us to build this architecture, right? So just another example. So this is all of this. What's important to note here is we are an open source first organization. So all of this you can do yourself. And later on, I'll have a QR code which will take you to a tutorial. So with a few commands in Juju, you can go and deploy an OpenSearch architecture with these different OpenSearch operators and different roles, right? So you can see here they have the different aliases for them, for the operators, and then we connect them all together with integrations, right? So again, picturing this graph, we're just kind of creating that network and responding at the edges of that graph to the events, right? So taking what we've learned and really applying that now, how do we create an open source RAG architecture? Well, Juju makes that really simple, actually. So we, again, just deploy OpenSearch. We configure the roles. So what we do here is we split the answer we think we have to creating a scalable RAG architecture is to split it into 3 parts. So, and that is ingestion, vectorization, and the LLM itself. So, where we can connect that all together with Juju, this allows us to independently scale parts of the architecture, right? So if we discover that for our use case, that ingestion needs a bit more, compute, we can add or remove. Or likewise, if we discover that it's a bit over provisioned, we can also remove units in our architecture. All of this is enabled with the orchestration engine. And of course, all of this is great, but how we need to monitor that, right? So, and how we do that is with integration to observability. So, we have our Canonical observability stack, or COS for short, and much of the same. We just create a COS deployment. We then expose that, and we then integrate that with our RAG deployment or our RAG architecture, our RAG deployment. Sorry. So this allows us obviously to then automatically monitor new nodes as they come into our graph, and also stop monitoring resources as they get scaled down as well. So the important thing here is we're just making sure that this graph is maintained and it kind of coalesces into the desired state for our RAG deployment. So we have a QR code which will take you through to a tutorial. So this will take you through a tutorial to try this out for yourselves. I'll just leave that there for a second. Okay, so what's the takeaways here? So an open source, secure RAG architecture that you can deploy yourselves in your home lab or in your organization. It's scalable and dynamic, so it's not like concrete. You're not going to pour it and it's going to be stuck. The important thing here is this solution is able to adapt to the needs as you discover them or as you refine your requirements. You can just add and remove those units or operators to a deployment. And of course, it's secure as well. So we enable things such as data at rest via dmcrypt in Ubuntu, and data in transit via TLS, and then data in use via confidential compute. So all of these things are enabled on the OS level, and then OpenSearch is able to take advantage of that. So we're from Canonical, but you probably know the most popular product, most famous product, Ubuntu. We're an open source first organization. We've been doing this for many, many years now, and we create open source and secure operators for OpenSearch. Thank you.
Thank you, Peter and Pedro. Nice talk. Question time. We have the first question.
Can you maybe say a few words about this concept of data cold and data hot? What is behind it?
Yeah, so this is just the idea of separating. That was actually one example, but it's the idea we could. Can you hear me? Okay, I was moving. So it was just one example, but on our operator, you can define roles. And we created a role of data.hot and data.cold, where you can define different types of storage backends for your nodes. So for example, you may have nodes that are faster, or you need to access that data more often. So you can call them data hot because they have drives that are just faster than others. So that's, we just separated, but it's a nomenclature that we have on the operator specifically.
Yes.
But for the search to work efficiently, I think at some point you have to have the decrypted data in some place, right? And can you maybe explain what is your assumption? What part of the architecture is secured, and what part, does have the decrypted data and is you have to assume that it's not attackable?
Yeah. I'll just go back here, actually. So when we talk about data at rest, the data that's saved on disk is encrypted, right? So that we will use standard process like tmcrypt. You can go on hardware with maybe your storage controller allows it, or the self-encrypting drive. And the data in use is when you save it in memory encrypted. So the data that's running on your CPU right now, of course, it's running on a safe place called enclave in the confidential computing, but that's decrypted for your process. Now, if you push it through the RAM, it will be encrypted. If you push it to your storage, it will be encrypted. But here is decrypted, right? And the goal is just to avoid you having essentially a non-encrypted RAM, and anyone can just dump that memory if they have enough access into your hypervisor and read that memory through that will contain all your keys and information that's relevant for you.
Any more questions? Okay, then I will ask my question. The operator that you were showing us, right? So how open source is it? And is it built on top of the Kubernetes operator, or is it a separate effort? Yeah.
So to the first question, yes, it's open source. It's Apache 2 licensed. It uses Juju as its control plane. Juju is a tool that we developed. Is a model-driven lifecycle management tool, right? So Juju is also Apache 2. So the whole environment is open source. You can download right now and start using and even contributing. Would be very welcome. And regarding your second question is, we use Kubernetes, but we are using Juju as our essentially control plane. So it's slightly different from the operator framework from Kubernetes itself. And for example, our operators is written in Python. So all the code is written in Python, Juju in Go. But we are always using Juju. The advantage for us is that we can deploy, for example, we can, in this scenario here, we could have, for example, the OpenSearch as virtual machines. Actually even better here. So this scenario is one very typical. We have OpenSearch as virtual machines, and then we have the monitoring running on Kubernetes, and that is all connected. They're just applications from the Juju perspective. It happens your underlying infrastructure skates on one side and a public cloud, for example, on the other. Juju won't really, it will change a little bit only.
Is there a OS dependency, the operating system dependency?
Operating system. So right now it's done in Ubuntu, but I mean, any operating system that we don't test on other operating systems, so just to be clear, we only test with Ubuntu. We had we had operators that were written previously for CentOS, for example. Any operating system that's using systemd would be systemd if it's a VM. Kubernetes will, of course, be our images. But any operating system that's using systemd would be a good candidate. We just don't test right now on them.
Understood. Thank you. Yeah. Any more questions? Anyone? Then, thank you very much. Nice
Thanks.
talk. Yeah.